Okay, well, welcome to the latest in the fMRI summer course. This is supposed to be advanced MRI and fMRI acquisition methods. It overlaps quite a bit with the presentation that Vinay gave on last Friday. How many people in the audience were actually here for his Friday presentation? Okay, so I mean, I think it's somewhat different. So I think there's some overlap and some differences. So that's probably good. Okay. All right. So the outline for today's talk is basically I'll quickly review the basic MRI, NMR physics underpinning MRI. And then I'll go on to talk briefly about the MRI imaging tools and techniques. And that's probably the extent to which it overlaps with Vinay's talk. And then I'll go on to sort of more into the actual sort of nuts and bolts of actually doing imaging, talk about case-based trajectories, and then if we have time, talk about controlling the image contrast and maybe some other stuff as well. Okay, so looking in a little bit more detail about the NMR physics basics, we're going to use the classical view of NMR. We won't be doing any quantum mechanics things here. We'll talk a little bit about excitation reception of MR signals and what the nature of the MR signal is itself, and talk about relaxation mechanisms. Okay, so in the classical viewpoint, we're not dealing with individual nuclei. We're talking about NMR. NMR is fundamentally about the nucleus of the atom, but we'll be dealing with collections of nuclei. But the signal is coming from the actual nucleus of the atom, and it occurs in the presence of an external magnetic field. And the nucleus is related to the intrinsic spin of the nucleus, and it's related. And the reason it's termed resonance is that it has a very specific resonance frequency at which energy is absorbed or emitted. Okay, so we have positively charged nucleus in the atoms, and we'll be dealing exclusively with hydrogen nuclei. So there's only one proton there. So sometimes we use the term proton interchangeably with nucleus. And in presence of a magnetic field, we basically develop a magnetization. And the magnetization absorbs radiation at a specific resonant frequency, and this is really the most important equation for us, is omega equals gamma b. And here omega is the angular frequency of classical magnetization, and that's 2 pi nu, where nu is the regular frequency. So basically that's just essentially a very simple relationship between the angular and regular frequency. Gamma here is the gyromagnetic ratio, and B is the magnetic field strength. So basically, if you put it in a bigger magnetic field, it spins faster. Okay, so for protons, or hydrogen nuclei, people will often say that gamma is 42.58 megahertz, but technically, of course, that's not an angular frequency. So that's actually referred to sometimes as gamma bar, which is gamma over 2 pi. Okay, so if the gyromagnetic ratio is 42.58, then at 1.5 Tesla, which is what the old standard, I guess, for MRI systems, we'll be running at 63 megahertz. Most of the systems we use are 3 Tesla, so we're typically around something like 127 megahertz. And we also have a 7 Tesla and maybe a second one later, which is at around about 300 megahertz. Okay. So the magnetization itself, M, is we think of it as a vector. M is having 3 components, mx, my, and mz. The magnetization vector itself at equilibrium is aligned along the main magnetic field, B0. Okay. Oops. So at equilibrium, the magnetization vector is basically M is 0, 0, M naught, where M naught is the amplitude of the magnetization vector. And this is a little bit complex, but basically I wanted to show that M0, how much magnetization you have is dependent on a number of things. N here is the number of nuclei you have, relevant nuclei you have, gamma, of course. B0 is for magnetic field strength. So this is why there's this push to go to higher field strengths, because we basically get more M0 at higher field. And I guess there's a temperature dependence as well. So in principle, if you cool the sample down a lot, which you probably don't want to do in case of people, you can get an improvement in the M0 as well. Okay, so if this M0 vector, which is initially, as we said before, aligned along B0, if it's ever tipped away from B0, it actually precesses around the main field at omega equals gamma B. So once excited, it'll just spin around that at some frequency. Okay, so that's a little bit inconvenient to deal with. So we often work in the rotating frame when we think about how NMR works. And we work in a frame that's rotating also at omega equals gamma B. I said it was an important equation. Okay, so if we work in a rotating frame, that means we're spinning around with the magnetization. Okay, so we're basically on board with magnetization as it goes around B0. Then we don't see the precession of M0 anymore. We're basically riding with it on the magnetization itself. So if we start in the rotating frame at equilibrium, here we have our M0 vector. If we now turn on a B1, so this is different from our B0, which is our main static magnetic field. If we now turn on a B1, which appears to be constant because we're in a rotating frame, but in the lab frame will be spinning around at omega naught, then basically, because omega equals gamma B, so now we can apply the same omega equals gamma B for the B1 vector, and we see that we get a new angular velocity, omega 1 is gamma B1. And which this causes the magnetization to rotate towards the y-axis, because the magnetization will spin around this. Will spin around this B1. And it's much easier to understand how this works in the rotating frame than it is in the lab frame, because it's all confused by the spinning around the z-axis in that case. So we've applied our B1, which is this B1 pulse, and caused the magnetization to rotate around the y-axis. Now, if we can control B1 and we choose to turn it off when it's only rotated a small distance, then we'll obtain a kind of flip angle where the M0 vector is tipped away from Z by a specific angle, which is called the flip angle with respect to the Z-axis. And then after we turned off the B1, the magnetization then precesses, i.e. starts spinning around this vector in the lab frame and returns back to equilibrium eventually. So all that was basically all in the rotating frame. But what it amounts to is that when we apply that B1 pulse is static in the rotating frame. So it's basically a very fast rotating magnetic field in the lab frame, and it's rotating at omega naught, in fact. Okay. So okay, so I'm lost track of something here. Okay, so as the magnetization returns back to equilibrium, the magnetization now has multiple components. It has an MX component, MY component, MZ component. So MZ is known as the longitudinal component. That's the component along B0. And MX and MY are transverse components. Now, the signal we see from NMR is proportional to MXY. We don't see anything of the Z component. And basically what's happening is, as the magnetization precesses around the Z-axis, it induces a voltage in a pickup coil that's aligned inside the magnet. And we pick up a signal that we can consider to be a complex valued signal, MXY, which is basically MX plus IMY. So how does it relax back to equilibrium? So the MZ component, the longitudinal component, is observed to be controlled by this relaxation equation. And what this is saying is basically that the MZ component changes, the rate of change of the MZ component is proportional to how far we are away from M0. So the closer we get to if we're far away from M0, say here, we relax towards M0 very quickly. So our rate of change is quite high. And as we get closer and closer to the equilibrium value M0, the rate of change becomes slower. And so if you solve this equation, it's very simple. You basically end up with this equation here, which is saying that the magnetization Z at time t is equal to M0 plus, and this is how far away you are from M0, and that distance you are away from M0 is decaying like an exponential. And a different way of writing this, trivial rearrangement of the equation, is to say that mz of t is the initial magnetization. So if you've got some initial magnetization, that component decays like T1, and the magnetization and a sort of a fully recovered magnetization grows like T1 as well. So basically, if you and this will turn out to be important later, because representing it this way I find to be quite useful, because basically if you prepare some special value in your magnetization, if you somehow encode something in your magnetization, the amount of that encoding will decay like T1, and you'll end up with this unencoded magnetization growing back at the rate 1 minus e to the minus t over T1. So this kind of explains how you can use magnetization as a kind of memory store to store some prepared contrast value or something like that. So then you can basically store something for like several T1s of lifespan, because by that point the encoded information will be lost at rate e to minus t upon T1. Okay, so just looking at that again, this is a nice slide I was able to pick up from this paper here, and has some quite nice explanations as well. So basically you see that there's the magnetization is tipped over to 90 degrees, and then it recovers just like we saw in the previous diagram, and it recovers back to the equilibrium value. So if you initially saturate magnetization, I put it exactly in the transverse plane, and you wait the T1 time constant, it's basically recovered to 63% after T1. Which is a kind of useful rule of thumb. Okay, what about the MXY, the transverse component? Don't forget, this is the component that actually is responsible for giving us the signal. Well, this is controlled by this equation. It's a little bit simpler, and basically it basically says that the MXY component decays at a rate T2 exponentially towards 0. Note that everything that T2 is always less than or equal to T1, and sometimes it's quite a lot less. It can be an order of magnitude or more or less. So basically, that means that our MR signal dies away faster than MZ regrows. So if you think about the magnetization vector, it's not like it rotates. When we initially tipped it down, when we initially tipped it down like this, we tipped it down. It would follow the magnetization tip would have followed the sort of arc of a circle as it came down, assuming we tipped it quickly enough. And then, but when it decays back, it doesn't decay back along the same path. It basically typically shrinks a lot faster in MXY than it does grow back along MZ. So it follows some kind of course like this. And that's a little bit unlucky, because we would like to be able to use our MR signal for as long as we'd like, for as long as time as possible. And then when we've finished using it, we'd like to be able to scan again. But unfortunately, that means that our signal dies away, but it might be some time after the signal's died away before we can have another experiment to run again. Okay, so what's that? Oh, okay. So in addition to the T2 relaxation mechanism, in any given voxel, we're likely to have a slightly inhomogeneous field. And so this means that even if ideally the signal would have decayed like this T2 relaxation curve, in practice, because the magnetization in the voxel is experiencing slightly different background fields, but it turns out the magnetization gets out of phase rather quicker than that, and so it actually decays in practice at a rate called T2 star. So T2, the T2 is generally, you can think of it, if you like, of the T2 is the actual sort of tissue property, and T2 star is to some extent a sort of is dependent on the size of the voxel and the sort of local environment of the voxel. So if it's an inhomogeneous field, then the T2 star would be quite significant. But T2 has probably got more, in some ways, T2 probably has more, it's more like a real physical property that's reproducible. So it would be nice if you could recover the actual T2 value. And one way you can do that is by forming a spin echo. So if you imagine your magnetization is initially at equilibrium and you tip it down and then it dephases like this T2 star effect, which we just saw. If you now apply a 180-degree pulse, that'll essentially cause all the spins here to be flipped over. This entire disk, if you like, will be flipped over if we apply, say, the 180-degree pulse along Y, then that will cause all these spins to flip over. And now, instead of dephasing further, these spins will now return back to their original start point, and you will end up with something called a spin echo here. And this will, if there's a 180-degree pulse played here, the magnetization curve here will then recover back up, and you'll and sort of just touch that T2 curve again before starting to fall away again. Okay, so that's just the basic NMR background. And now I'll just briefly go over the MR tools we'll need for imaging to make images. Okay, so the most fundamentally important tool of the MR scanner for making images is the magnetic field gradient. Okay, so our main magnetic field was B0, and we have omega equals gamma B0, which I can't stress enough. We superimpose now an additional magnetic field in the same direction as B0, actually. But it's actually a field gradient, G, which is a vector quantity, Gx, Gy, Gz, that should say Gy. And then we will see that we have an additional frequency, omega equals gamma Gx x plus Gyy plus Gzz. So basically, the G is the sort of spatial derivative of the magnetic field that we've applied. Okay. So if we just look to, I mean, basically you have a simple relationship that when you've got a magnetic field gradient G and you're in the x direction, your actual offset frequency at the center of the magnet is 0. If you move out further in the x direction, you've got a positive offset field, and so you end up with a positive offset frequency. And if you go the other way, you end up with a negative one, and equivalently for y and z. And it's important to appreciate that these gradients are all in the direction of the main field of B0. We always represent that along the z direction. Okay, so just before I finish that, I was just going to say that the gradient fields are typically, a typical gradient field used in a human imaging magnet might be something like 30 millitesla per meter. So that would give you 3 millitesla at about 10 centimeters from isocenter, which is kind of the magnetic fields you might experience. So it's basically about 1,000 times smaller than B0, just to kind of give you some kind of appreciation of the scale. So it's important to appreciate that the magnetic field, these magnetic field gradients, still make magnetic fields in the same direction as B0. So here's our magnet. It's meant to be a kind of a walls of our magnet cut away, and we've got our main field B0 along the bore of the magnet. And then if we apply a gradient in plus x, we'll end up with, basically on the right, we'll end up with a slight addition to the main magnetic field. In the center, we'll have B0, and on the left, we'll have a slightly reduced magnetic field. Now, remember, of course, it's only really like 1 in 1,000, so it's not like it's not as dramatic as it's shown here. But basically, you can see that the magnetic field is still all in the z direction in all cases. So you can have a magnetic field in plus x. You can have a magnetic field in minus x. You can have a magnetic field in the z direction. So it's enhanced the strength of the magnetic field further along z and diminished it further away, but it's still all in the z direction, and vice versa. And if you combine gradients in x and z in various combinations, you can actually end up with magnetic field gradients in kind of diagonal directions. So you can do, and this is the reason why you can do oblique imaging, and you're not restricted to only doing scans in kind of the three canonical planes. You're not restricted to axial or sagittal or coronal scans. Okay. So let's now consider slice selection. So supposing we've got subject in the scanner, okay, here, and we wanted to take an image of this slice here. So let's say we put on a magnetic field gradient here, and there's some position Z in the scanner where the slice of interest is. Okay, then we know that because omega equals gamma B, we basically know that the offset frequency for that slice is gamma gz dot z, right? So we basically put a gz gradient on, and for the slice of interest we want, we can figure out what the frequency offset is. So when we did our excitation previously, we had our B1 pulse, and that was going around at omega 0. What this tells us is we basically need to offset the frequency of that B1 pulse by some delta omega, and then that'll move our excitation. Instead of just being an excitation at omega 0, it'll now be an excitation at omega 0 plus delta omega, and then we'll get an excitation along a thin slice along this direction. Okay? Now, because of the duration of the RF pulse, there's some definite bandwidth to that pulse. But we can actually shape, by carefully choosing the shape of our RF pulse, we can excite a band of frequencies that defines a particular slice with a particular slice width. And so this is the classic way to do this is basically to take a Fourier transform of the pulse shape you want. And so if you wanted a slice with uniform slice across where basically no spins are excited outside the slice and they're uniformly excited within the slice, you would have a square pulse, and you take Fourier transform of that, and it gives you a sync shape. Now in practice, that's not quite the right way to see it in technically, but it works pretty well for small flip angles, and it even works quite well up to 90 degrees actually. So here's a sync pulse that's been truncated. And when you actually run the simulations of that, you can see that the magnetization that actually gets excited looks like this and needs rephasing. But so you apply an additional gradient term to unwind it. But basically, when you play this excitation pulse out on the scanner, you end up with a slice profile that looks like this in space. So this is basically your offset frequency, or if you like, it's a position along in the z direction, say. And you end up with getting a slice profile that's fairly well defined here, with some kind of sort of a slight outer slice ripple out here. And this is what happens to your MZ. Basically, you have a notch in your MZ where the slice was excited because you've used up that magnetization in that place. Okay, any questions at all? Okay, I will carry on then. Okay, so that's basically how we do our slice selective excitation. So when we run a scan in the scanner, if it's a 2D scan, or we have multi-slice 2D scan, basically the scanner will repeatedly, one after another, excite slices in the scanner by varying this delta frequency, this delta omega frequency here, and this band will move around, and it'll move from one side of the head to the other, and then we will just repeat that over and over again. Okay. So the next tool we have to discuss is the gradient echo. So let's say we've excited our slice, and there's a question of what we can do with it. So it turns out that if you have a gradient pulse, when you apply it, of course, one side of your voxel is will be when there's a gradient on, one side of your voxel will be spinning slightly faster than the other side of your voxel. So the spins in your voxel will become dephased. Now earlier on, I showed you a spin echo, which we refocus things using an RF pulse. But you can actually, if you're in control of the inhomogeneity, which is basically caused by the gradient, then you can refocus the spins basically by applying the same gradient in reverse. And here, the amount of dephasing is related to the area under this gradient. So what you end up with is when the gradient area matches, you end up with the spins initially become dephased and your signal dies away. And then when you reverse the gradient, it comes back together and you form this kind of gradient echo signal, which is around about here. okay? And that will turn out to be quite useful later on, okay? Okay, so those are the basic tools that we'll be using to make our MR images. Okay, so now I'm going to go on to case-based trajectories, okay, because this is basically a sort of general approach to MR imaging. So in the main magnetic field, B0, we have omega 0 because gamma B0. Now, if we as we said before, we superimpose a spatial magnetic field gradient G, and we end up with this offset frequency Gx, Gy, Gz. And so that's basically going to give you an offset frequency G dot R, if R is your position vector inside the magnet. So let's consider this phantom here. And we can look at this little green blob of tissue at some position R in the magnet, okay? So R is X, Y, Z here. So let's just look at, say, the GX component. So it's very much like the slice selection case, but basically we've got some piece of tissue here at some location. It's already been excited by an RF pulse, and it's sitting there in the magnet, and it's processing away. We turn on this gradient, and it now starts processing with some additional frequency, gamma G dot R. And if we vary the speed of our gradients, the precession frequency will also change, because basically, assuming that our spin is constant, R of t is always R. G of t is time varying if we choose to turn our gradients on or off, or vary the amplitude. Okay, so it's interesting to consider how much phase this little blob of tissue accumulates over time if we've got some gradient waveform. So G of t over time is called a gradient waveform. And so over time, the phase of R will accumulate basically as the integral of the local frequency. So we have gamma is constant, integral 0 to time of G of t dt dot R. And R is considered constant here, so it shouldn't really be R of t. Okay. So what does that look like across our whole slice? So this is our slice of interest. Well, the signal we'll end up with is basically going to be the integral of the across the whole image plane. Okay, so we've got a rho of R here represents the number of the amount of magnetization. It's basically the magnetization density across the slice. So it's basically how much magnetization there was to start with across the slice. And this is this is an exponential with a e to the I theta type term. So it's basically a complex exponential, and with a phase term that's given by this delta theta here, in here. So basically we have the integral across the entire slice of the proton density with this phase term. So if we now write k of t is this term in here, so this is basically the time integral of the gradients with a constant factor in front of it, we can now make this signal equation look like this. And this is a very well-known expression. This is basically a three-dimensional or two-dimensional Fourier. It should be a two-dimensional, I guess, because it's a slice. Two-dimensional Fourier transform with respect to k. So it's a space. So if k is our so if rho is our magnetization density across our slice, then we're basically finding that the signal with respect to k is a Fourier transform of our spin density, and so we can invert this to obtain our spin density back. So basically, this is the essence of MR imaging. Okay. So this is a well-known operation called the Fourier transform. Okay. So here's our signal acquisition equation. We have k of t is the time integral of gradients, and basically our strategy is going to be that we need to sample all the points in k-space to acquire sufficient data for image reconstruction. So basically we need to collect samples from all these grid points around here. And we initially start at the origin here, which is a green dot. And k of t is the sampling position at any given time. And if you like, you can think of g of t as the velocity through k-space. So what we have to do is basically modulate our gradients to drive the green dot around this space. And as we go along, we'll collect data as we go. We'll just pick up the MR signal. And if we can sample all these points, we can then take a inverse Fourier transform, and we should be able to recover our image back. Okay. A couple of points of interest are that, well, as I say, g of t is essentially velocity through k-space. And the sampling spacing, so the intersample spacing here, is essentially what determines your field of view. The delta k between these two samples is essentially one over field of view, and the entire extent of the k-space region we cover essentially determines the pixel size. So if we want smaller pixels, we have to have a bigger k-space, and so it generally takes more time. Another point to consider is that g of t, our gradients, can't be arbitrarily any waveform you like. They're basically limited because of the physical constraints of the capabilities of the MRI scanner and the limitations on the gradient amplitude and the slew rate that can be applied. So that also limits the rate at which we can traverse this trajectory through this space. Okay, so some other properties of k-space that are kind of interesting are that if you have points near the center of the k-space, the data samples that we collect near the center of k-space, these represent essentially low spatial frequencies. So this is the k-space sample here, and essentially this reconstructs to a low spatial frequency. A point near the edge of k-space reconstructs to a high spatial frequency. And as you go in different directions, these patterns change orientation as well. Okay. Okay, so remember our gradient echo. So this is going to turn out to be quite useful now, because if we apply our gradient echo formulation, which we had a little while earlier, we can play our RF excitation here, and then we can apply a gradient pulse and then reverse the gradient and bring it back and make this gradient echo. And now we can kind of see why you get this echo signal as well. Another reason why we get the echo signal, because this initial gradient pulse, remember g is the velocity through k-space. The initial gradient pulse here will drive us to the left-hand edge of k-space because it's like a velocity in a negative direction. And then we reverse the gradient and go the other way, and we sample as we go, and we collect this echo. And as we cross through the middle here, we get the echo peak. And that's considered a time to echo for a gradient echo sequence. And so we've got these little dots here represent sort of collecting samples. Okay. So what's another thing we can do? We could just pulse a gradient at different amounts, and we could end up offsetting in the negative direction by different distances, or in positive different direction by different distances. So that's another tool we've got. So if you combine those two together, you can basically have a sequence where you have an RF excitation, you have a gradient echo formation, and you have this offset in the phase encode direction. So you initially start at the middle. This gradient here will drive you to the left-hand side of the k-space. This phase encode step will, on the first time you apply it, will take you down to the bottom here. So you end up going to the corner, and then you read out and you collect a line. On the next time, you repeat the experiment again, and this time you use the next step up of the phase encode gradient, so you end up one less, and you read out again. And you repeat this over and over again until you've fully sampled the whole k-space. Then you can put it in your Fourier transform, and you can get your image. Well, that takes a long time, so who wants to do that? So when we're doing fMRI, we typically want to go fast. So we have this thing called an echoplanar imaging, which is basically collects the whole thing in one go. So we now have our RF excitation, we have a slice selection on that, and we have a gradient that makes a gradient echo and then turns it round, because this is, of course, the speed through k-space or velocity through k-space. So we have our initial offset in ky, or second gradient direction, and we turn it round and we read out here, and we get an echo. Well, and then we have a little blip of gradient just to kind of drive us up to here. We flip the gradient over, and we read out in the other direction, and so on and so forth. And it's kind of like mowing the lawn or ploughing a field. And in fact, it's actually this pattern actually has a name for it. It's called a boustrophodon, but nobody ever calls it that except me. So, okay. So you can imagine various other encoding strategies too. But most of fMRI, we're using this boustrophodonic trajectory, basically. So you can have spirals and you can have Lissajous figures, but the vast majority of fMRI studies are done using this. Okay. So now we need to sort of consider some of the mechanisms by which we can control the image contrast. So when with gradient echo and spin echo sequences, there are, if you have a short TE, so if we come back to our gradient echo sequence, if TE is short, as is represented here, basically if the echo is read out very close to the RF excitation and the TR is long, then you'll have full magnetization recovery, and then you'll excite the magnetization and almost immediately read it out, so there won't be very too much T2 star decay. So then you'll end up with a signal that's very much like proton density. If, on the other hand, you have a long TR and a long TE, then you'll have a lot of T2 star decay, so you'll be much more sensitive to the different susceptibility areas which the magnetization's in. Okay, and there's a similar argument for spin echoes too, that if you have a much longer, if you have a long TE in a spin echo sequence, you'll be more sensitive to T2 because you'll have refocused the T2 star effect and you'll basically be on that T2 curve again. Okay. So those are essentially intrinsic, those are essentially the intrinsic contrast of the imaging sequence. Another powerful way of introducing contrast into the MR signal is to use a contrast preparation module. And there's a whole lot of those that you can use. So you can apply, for example, a fat saturation pulse, which will selectively destroy only the signals arising from fat. You can have flow preparations or diffusion preparations, which selectively prepare the magnetization and create a sort of longitudinal magnetization reserve with a particular contrast in it. And as I was saying at the beginning, that contrast will stick around for about some kind of multiple of T1, because it'll eventually die away by T1 before you have to re-prepare it again. One particular sequence that I think is particularly relevant to mention is the MP RAGE sequence. So this is typically used for anatomical scans, and it provides a gray-white matter contrast. And it's basically a 3D sequence, so it doesn't use slice selective excitation. Well, he uses a slab selective excitation, so he uses a slice which is very wide, but then uses a 3D K-space encoding. And the way it works is it basically has an inversion recovery preparation pulse, so it actually applies a 180-degree pulse, and then uses multiple imaging readouts. So there's multiple imaging readouts for every inversion pulse. In fact, there's a diagram here. So this is a 180-degree pulse, and it generates some inverted magnetization. It inverts the magnetization. While that's, there's then a an inversion period here, which is known as TI, the time of inversion. And then there's a imaging readout here with a small flip angle pulse, which just samples that inverted magnetization. And this is basically applied over and over again. So if you look at, here's the inversion pulse, and then you've got all these little gradient echo readouts supplied here. They're all very small flip angles, so they just sample that inverted magnetization. And basically you provide all, you collect all your, say, Z direction encodings of your phase encodings here. And then when you've collected all those, you have to wait for magnetization to fully recover again so you can invert again and repeat the experiment. And this is very typical of what a pulse sequence it looks like when it's when it's a magnetization preparation based sequence. ADC? Sorry, over here. Oh, ADC is the acquisition, basically. It's the analog to digital converter, I think, is what it's basically saying. When this is when the data sampling is active. Is I think what it's supposed to represent. This is taken from the from one of the MPVage early papers from like the early 90s. Okay, that's pretty much what I have. So, are there any questions? Yeah.
Are there any contrast separation modules that are very sensitive to cerebral spinal fluid for visualizing that?
So that's I think you can imagine what it would take to make something like that, because basically it's essentially liquid, right? So it's you can easily, for example, liquids typically have long T2s, so you could imagine that something like a T2 preparation module would be useful for that. Yeah, I should probably put more in about these things. Yeah. So there's a whole lot of things that I haven't actually covered in this. It's difficult because there's so much potentially to talk about. So parallel imaging would be interesting, and more on diffusion imaging. But I think there'll probably be talks about diffusion imaging later in the series. Any other questions? Cool. Okay.
So, if you were doing like in a 70, you can test the cerebellum with gold imaging. Is there a reason why we always go axial? Why not acquire? So, for instance, if you want to have short PRs and you want to focus entirely on the cerebellum, you could go. Let's say you were interested in the cerebellum and the motor cortex, right?
Yeah.
You could get it totally structured with your angle, get a sort of oblique application. That's something that's going to be problematic in 70.
I have no experience in that, but I imagine that it would be okay. No. Sean's shaking his head, so maybe. Yeah. Okay. So you're saying it's not a problem. Okay. Okay. Because I can't imagine it would be. I think that would be okay. You can. Yeah. Yeah. And essentially, there's not really any really preferred directions in MR, so you can usually choose your directions. There's no sort of systematic preferred directions, so you can usually choose your orientations of slices and so on to help with things like, for example, because there's limitations on the field of view, or because basically if you want a large field of view, you might end up having to encode for longer. So just to collect stuff you don't really want, right? So you're free to. There are certain directions which are preferred because for that, because you can, for example, use a slab selective pulse to cut out certain directions. So when you do your excitation pulse, you can restrict the field of view by only exciting a slab or of a definite size. And when you read out in a certain direction, you can restrict the field of view there because you can apply essentially filters on your readout train. You can apply filters, so you're free to sort of play games with the, even if you want a certain slice, you can then play games with how you acquire it within the slice in order to sort of restrict the field of view, and that maybe help you with speeding up the acquisition. Okay, well, in that case, sorry, one more.
You talk about the issue of motion in MRI. How do you suppress the motion problem?
Yeah. Okay, so there's all kinds of different motion. So are we talking? If we're talking fMRI, there's still several kinds of motion. So for a head, a lot of the time, you're dealing with kind of rigid body motion. You can kind of model it as a rigid body, and that works reasonably well. So for a lot of things, but not for everything. So if it's a sort of gross, and you can model it as a rigid body, you can often, well, the easiest thing to do basically is to suppress it by padding the subject in really well, but everybody knows that, right? So there are some methods which involve using MR navigators, basically that acquire additional data. In addition to the imaging data, they acquire some data which provides information about the subject, either the subject motion directly or about the orientation of the object at a given time. And you can compare, if you've got real-time processing, you can either compare those data to like your previous scans that you used to combine to make your image, and then either choose to reject the data and reacquire it, or if you need it in real time, you might be able to make a motion correction in real time, applied back. That's quite fairly sophisticated and requires a fair amount of engineering to make that happen, but it can be done. There's usually a little bit of latency involved. And so the concern a little bit is that if you have too much latency, if it's a kind of pulsar motion, you might end up being applying the correction at exactly the wrong time. But we, depending on, these things tend to be very sequence specific. So on some of the scanners here, we have a system called Promo on the GE scanners, which helps with the MP range scans. On the 3TD, we have a system, an optically based system, which we've been struggling to get to work well, but it's kind of got a camera, and in principle, it can track head motion and feed it back into the scanner. But well, it's still a bit of a work in progress for us. We're not getting results as good as we'd like to have with that.
So are there certain sequences that are better with motions than other, or it doesn't matter?
Yes, you can choose to tune your sequence a little bit for that, to help with that. That was quite popular back in the 1990s. Problem is, as you sort of tend these days, there's not a lot of sort of dead time in sequences typically to reacquire. So it depends on really what you're trying to do. I mean, if you're trying to collect a time series of data, it's basically it's happening now, and you have to kind of get the data now, and you're stuck with what you get, kind of thing, a lot of time. But in principle, if you've got plenty of time, if you're acquiring, say, an anatomical scan, you can choose to. I mean, you can make these measurements and reorder some of the scans, or you can gate, for example, if you've got respiratory motion, or you can gate to the either the ECG or the respiratory, or both, and try and sort of suppress some of these motion effects that way. Vinay?
Or those that like radial scans.
Yeah. So there's a bunch of techniques where you actually acquire gradient echoes rather than on a Cartesian pattern. You can acquire those gradient echoes and orient them through the center of K-space, so they form a star pattern instead of a grid. And those kind of methods tend to be a lot of effects of motion tend to show up in the phase of the signal you collect, and because if you collect an echo through the center of K-space, you can say to a certain extent that you can control the phase better, because basically the scans through the center of K-space are supposed to be like profiles, a bit like just like a CT scan. They can be transformed into something that's nominally a real valued thing. So you can then suppress the phase errors. And so those types of measurements are typically more robust to motion. So there's a couple of methods using basically radial scans or radial blades. So you acquire small rectangular strips with a kind of star pattern that all pass through the center of K-space, and they can be convected independently of each other and then combined together to make an overall solution.
Andy, could you say a few words with regards to the deeper NMR phenomenon that's sort of...
Yeah, so I mean, I was talking about things like essentially spectroscopy, magnetization transfer. Obviously I'm simplifying NMR enormously by just basically saying it's talking about sort of as though everything's just water spins basically in this talk. There's no attempt to sort of really deal with complex sort of spin-spin interactions and things like that. Yeah. Any more? Okay. Thank you.